Good afternoon. We are group 8. So I want you to picture this, okay? So imagine we are designing a medical device. Okay, let's say a life-saving medical device. We can take the heart pacemaker, for example, right? And suddenly the device starts sending irregular signals. The device becomes unstable. So what do? At this point, it becomes a life-threatening error. It's not just any random error, a random mistake. It can cost someone their lives, literally. So now the question becomes, as engineers or as biomedical engineers, how do we come up with a solution for this problem? Okay, so to solve this particular problem, I want to introduce you to one of the most powerful tools in control systems. I present to you the Wood-Hewitts stability criteria.
We are using the Raoult-Hewitts criterion to investigate the stability of the system. So first of all, we write the powers and the coefficients. So the coefficient of S5 is 1. Then you skip to S3 and the coefficient is 2. Then you skip to S, the coefficient is 11, but the rest is not there, so you write 0. Then you come to S4. The coefficient of S4 is 2. Then you skip to S2 is 4. Then you skip to 10 and it's 10. So the rest will be 0. Then we'll find the determinant of this one. So in finding for the determinant, it's 2 times 2 minus 1 times 4 divided by this 2. So you get 4 minus 4 on 2, which is 0 on 2, and it's 0. So the coefficient of S3 will be 0, and you pick this side and this side, and you use it to find the determinant. So it's going to be 2 times 11 minus 1 times 10 divided by this 2. And you get 22 minus 10 on 2, which is 12 on 2, and it's 6. So this side will be 6. And the rest will be 0 since the side is 0.
So since the first element here is 0, we are going to multiply 2 by s plus 1. So we are going to multiply s plus 1 2 by the characteristic equation. So you are going to get, all right, so you are going to group like this. So we have, all right, so after multiplying s1 2 by our characteristic equation, this is what we had.
This is a new characteristic equation. And from this, I'm going to derive the coefficients from S6 to S4. So just like the initial one, we are going to have our powers S6, S5, and S4, and have the coefficients here. So from this equation, our coefficient is going to be 1, 4, and 15. And for the S5, we are going to have 3, 6, and 21. So these are the coefficients for S6 and S5. So to find for S4, we are going to find the determinant. And for the first one, it's going to be 3 times 4 minus 6 times 1 all over 3. And for that, we are going to get 2. So the first one will be 2. Then for the second, we are going to have 3 times 15 minus 21 times 1 all over 3. From this one to, we are going to get 8. So our coefficients for S4 will be 2 and 8.
So I'll be finding the coefficient of the rest of the powers, which is S3, S2, S1, and S0. So to find the coefficient of S3, I'm going to find the determinant for, I'm going to take a 2 by 2 determinant for 3, 6, 2, and 8. And that's going to give me 2 multiplying 6 minus 8 multiplying 3. That's going to give me minus 12. So dividing minus 12 by 2, I'm going to get minus 6. I'm also, for the second coefficient, I'm going to take the determinant from using 3, 21, 2, and 10. So for that determinant, I'm also going to get 2 multiplying 21 minus 10 multiplying 3. I'm going to get 12 for that. Now 12 divided by 2 is 6. So I get 6 for the second coefficient. Now, by just observing the value for the third coefficient, using 3, 0, 2, 0 as my matrix, I'm going to get 0. For S2, I'm going to take the 2 by 2 matrix, which is 2, 8, minus 6, and 6. And finding the determinant for that, I'm going to get minus 6 multiplying 8 minus 6 multiplying 2. I'm going to get minus 60. Dividing minus 60 by minus 6, this minus 6, I'm going to get 10. So I'll get 10 over here for the first coefficient for S2. Moving to the second coefficient, I'm going to take my 2 by 2 matrix from 2, 10, minus 6, and 0. So the determinant for that, for the 2 by 2 matrix, which is 2, 10, minus 6, 0, the determinant for that is going to be minus 6 multiplying 10 minus 0 multiplying 2. I'm going to get minus 60 for that. That's for the determinant for the second one. So dividing minus 60 by minus 6, I'm going to get 10. Now, by observation, I'm going to see that the third coefficient, which map to S2, I'm going to get 0 for there too. Now I come to X1. So let's move to S1. So for S1, I'm going to take my 2 by 2 matrix from minus 6, 6, 10, and 10. So for that, for the determinant for that is going to be 10 multiplying 6 minus 10 multiplying minus 6. So the determinant for that is 120. 120 divided by this 10. I'm going to get 12 for the coefficient for the first coefficient for S1 is 12. Now the second coefficient for S1, by observation, I'm going to see that I'm going to get 0. So the second coefficient for S1, I'm going to take the 2 by 2 matrix, minus 6, 0, 10, 0. And just by observing, I'm going to get 0 for that. So here is 0. Now I move to S0. So for S0, I'm going to take the 2 by 2 matrix from 10, 10, 12, and 0. Now, finding the determinant for that, I'm going to get 12 multiplying 10 minus 0 multiplying 10, which is 120. So 120 divided by 12 is 10. So I'm going to get 10 for the first coefficient for S0. Now, by observation, I'm going to see that the second coefficient for S0 I'm going to take my 2 by 2 matrix from 10, 0, 12, 0, and by observation, I'm going to get 0 from that. So these are my coefficients mapped to S6, S5, S4, S3, S2, S1, and S0.
I'll be taking us through the implication and the usefulness of the complete Routh-Hurwitz table in determining the stability of the system. So now, the Routh-Hurwitz criteria makes us understand that we look at the coefficients in the first column only. Those are the coefficients we are considering. So now, the Routh-Hurwitz criterion also makes us know that the number of sign changes will determine the number of roots in the right-hand plane. So we look at the coefficients that map to s to the power 6. We see that from s to the power 6 to s to the power 4, there is some consistency in the sign, meaning there is no sign change, until we get to s to the power 3, where there is a sign change, 2 changes to -6, meaning we record our first sign change. Now, after that, the coefficients that map to s to the power 2, there is another sign change. -6 maps to, it changes to +10, meaning we record 2 sign changes. Now, the stability of the system has already been determined by the sign changes. The first sign change made us understand that the system is unstable. Now, the number of sign changes makes us determine the number of roots in the right-hand plane. Since there are 2 sign changes, meaning there are 2 roots in the right-hand plane. Thank you.
I'll be presenting on the applications of the Routh-Hurwitz criterion. The Routh-Hurwitz criterion is used to determine the stability of devices. Rather than using complex equations to determine the stability of devices, the Routh-Hurwitz criterion makes it easy. A real-life application of the Routh-Hurwitz criterion is in the designing of biomedical devices. The Routh-Hurwitz criterion is used to determine its stability, in the sense that when its stability is determined, the device will not be a device like the infusion pump will deliver medicine steadily within a given rate.